Let's welcome Rajiv and India to PyData Seattle today. They are both machine learning platform engineers at Lyft. So they'll be telling us about building machine learning observability pipelines. So let's give Rajiv Prabhakar and India Saha a round of applause and have them get started. Thank you. Good luck, y'all.
Thank you, everyone. Can you hear me well? Myself, Aninder, and he is Rajiv. I know it's just after lunchtime, so you had many options to go with your friends, to visit the lake, or hang out, but still you decided to come to this talk. So thank you for that. I really appreciate that. We really appreciate that. OK, so we will, today it's a hands-on workshop. So we have the slides here, and if you can go to this repo, we have the codes for that repo here. And there is a shared doc. I'm not sure how to share this, but this is the repo where you have everything for this today's code. So once you take a snapshot of this, I can quickly start. It's a 90-minute workshop, so we do not have a visibility like what's the machine configuration of each of you has. So in the README, I mention like what kind of configuration we are expecting as a Docker desktop. But even if you do not have it, don't fret. Just listen to the principle and the fundamental workings around it. You can try it at home after this talk or when you have time later. But specifically, we are looking for a Docker desktop which has around at least 4 to 6 CPUs. And you have at least 32 gigs of RAM on the Docker desktop. And if you can bring up that, I will show you live how to do it. And it's also on the PyData conference abstract. The link is also there for the GitHub repo. OK, so let's start here. So you already got introduced, and so we will talk about the agenda first. So here we will say why did we need to build an anomaly detection system at our company, and what are the challenges because the data is at scale. So we can work with Pandas data frame on notebooks, but how can we scale it up? So we will talk about the pain points and what did we do to mitigate those pain points and what are the solutions we used. And the second demo would be like using statistical packages such as stats forecast. And we will specifically deep dive into the algorithm that we use and some of the tweaks we make to make anomaly detection at scale. And the third part will be a little, maybe 2 to 3 minutes talk, like what we learned along the way. We will try to keep it simple and short so that everyone can follow. And we'll have questions and answers in between as well, and you can also ask like at the end of the talk. So here are the resources again. We also released 2 blogs about what we are talking today. Once we share these slides, this will be available to you. OK, so let's talk about the problem. So in general, in any ML platform, in any company which uses ML platform, you will get so many models deployed. And many inference requests, millions and hundreds, we have like billions of requests coming across many models. Even if you make a one ride request, there will be 10 models at least working on it. So think about like millions of rides. So we capture all those inference requests. Essentially, we are instrumenting the inference request and logging into some kind of database in the backend. It can be some SQL DB or Hive database. But the problem is not all models get the same number of requests. Some models are very popular. Some models they are not that popular. Some models get requests more in the peak time in the day. Some models get more requests during the night or the evening. It depends. And the second problem is not all models have the same kind of features. Some models have more numerical features, less categorical. Some has just the reverse. And some models maybe have 10 features, some has 30 features. We just cannot know as a platform engineer. So what can we do? What can we do about that? So since all the inference requests are so wide and so varied, we do not have a uniform way of processing them. How can we glean out metrics or statistics out of them in a more uniform manner? Because the number of features is not fixed, the feature types is not fixed. We do not know the feature names. The amount of requests or the amount of data coming in is also not same. Some has like maybe 10 GB of data coming in one day. Some may have like 1 GB of data coming in one day. And even the hourly patterns are different. And there is seasonality in the model predictions, inference requests as well. So how can we mitigate that? So our today's talk is about that. Given this variety of large number of models and these models keeps on growing, is there a unified approach of tackling this problem, or is there a simpler solution? So the solution we used is ylogs. We investigated a couple of open source as well as proprietary products for model monitoring, but we felt that ylogs fit our bill perfectly. There is a diagram here, a schematic diagram. Think about it in real life, what it happens. Like we have model raw logs or inference logs coming in every day, day 1, day 2, for model 1 and model 2. And so if we could profile this data, what does profiling means? Profiling means you take a snapshot of the features coming in. What is that what is the snapshot? The snapshot will contain the mean, the standard deviation, minimum value, maximum value, cardinality of the features. And the data keeps on coming. And we cannot just sit and wait like I process it one day and the next day also there will be like lots of thousands of data is coming. So how can I process them incrementally? It's not that it is fixed. It's every day it is growing in size. So we investigated ylogs and we found that first of all it is open source from ylabs, and second thing is ylogs gives a feature that you can take any features or any predictions. It may have n number of features, n numerical, x numerical, y categorical feature. You still can profile all of this data and create a binary out of it. And what does this binary has? This binary is nothing but the profile of the data or the snapshot or the statistics of the underlying data. And it will be clear when we have a real example. And the second point is, even if we profile it, today we need to again do that. So every day I'm getting a data. How can I get a profile for the entire month? Should I wait till the end of the month and process the entire data to get the monthly profile? Or is there a way I can profile every day and I keep on merging the profiles every day to create an overall profile at the end of the month? Or every day I keep on updating that profile so that I don't have to do a lot of work at the end of the month. At the end of the month is still one day's job, but I merge all the previous profiles. ylogs gives that benefit, and it supports Spark as a backend engine. And you also use Fugue, which is an open source abstraction layer on compute engine. It can support Spark, Ray, or any other compute engine. And Fugue helps us to abstract this profiling mechanism using ylogs. So it will be clear in a demo. So now we will go into the demo straight away. Before I go into the demo, is there any question I can answer? So to start the demo, once you go to this GitHub repo, it is very simple, straightforward. We have a Docker image. Everything is inbuilt into that Docker image. So you can open your favorite terminal just like I'm doing now. Let me know if the fonts are clear or if the fonts are legible. So we will run this Docker image. It is a publicly available Docker image, so anyone can use it. So while the Docker image is coming up, so let's go here. And open the Jupyter Notebook terminal, and there we'll have our entire demo. By the way, all the codes are coming from the GitHub. There is nothing like here which is not in GitHub. So we will first show you, so it will be divided into two parts, as I mentioned in the beginning. So we will have one notebook for distributed profiling, and the second notebook for actually using the statistical packages. So if you see in the notebook, in the Docker, there are two files named the same. What is this for? So I will be using this demo, which is like all the cells are empty, just in case anything happens with live demo and demo gods are not in favor. I can revert back to this cell where everything is already executed and you know the output beforehand. All right. So we will okay, I will minimize this window. Try to minimize. Okay. Oh, okay, cool. Okay. So some customary housekeeping job, Seaborn and pandas. So now I will, this is a kind of real data that is taken from one of our logs. Of course, features names have been changed for security purposes, and yeah, and we have like massaged the data a little bit. But the bottom line is, let's assume how does a real data would look like. So this is a model data. So our inference request came at this point of time, and this is the name of the model. And look at the requests. It's like a JSON structure, a simple JSON, because we don't know the number of features. We don't know the we don't know the type. So we persist everything as JSONs. It may be 100 features, it may be 20 features, it may be 1,000 features. It doesn't matter. Everything is just a JSON. So once you have those JSONs, so these are like the values of those features. Of course, the features have been like obfuscated here. So we get the data from the Hive table, or let's say we have a local S3 bucket. Now we want to extract these features because these JSONs are not valuable. I mean, JSONs are valuable for storing, but for processing and profiling, we cannot work with the JSON. So we need to extract the features. So how can we do that? We take that column, and then we do a pandas data frame JSON loads, as simple as that. And if we do that, so we make a small function that, given a big data frame, can I process individual rows and pick out the features? So I will execute this cell while I speak. So we are trying to say, can you think, before going to scale or big data, can you think of ways, or tune your thought process in a manner that, can I break down my problem into the most unit operation which is independent of each other? So in this case, one row processing is the most unit operation. And if I can make it work for one row, I can make it work for a million rows. So the responsibility of making it work on million rows is the duty of the computation framework, not mine. My job is to make it work on one row. So that's what we are doing. We are loading each feature, and then if we transform it, we will get something like this. So all the features have been transformed because there are like six features in this JSON. So feature 5, 6, so they are arranged in a haphazard manner, but when we transform it, we get this feature. So now what we do, we have features, but we also need some other data as well. So we concat with the original data, demo.df, and then now we get a very holistic picture that this is my model, this was my JSON, and these are the features I had. Of course, I don't have column names here. I will fix it in the next method. So the goal we designed this notebook is I will show you what we are doing, each individual piece, and then take all individual piece and put it into a function, a unit of work. So this is what this is called. It is a unit function to work on a partitioned data. So let's assume that your data is too big to fit on one machine. Even it cannot fit on like 10 machines. You will have many executors or processes. Can you write one function that will take each row, even it is distributed in many machines, each row and convert it into my features and the model? So when we put everything here, so you see that I have actually copied pasted what I have showed right now. I have copied pasted JSON loads, and I have pasted it sorted things like that. In addition to that, I have added some more extra model features, model variables, and then I have done the same concatenation again. So I did not do anything which is not I showed you before, but I just made it like one function. And if I can run this method, extract features, and I pass the entire data frame, I should be getting it for all the rows in the data frame. So while it is running, so let me wait for the results to come back. So if you see that since this data frame was around like 300,000 records, I processed it like within like 15 seconds live in this demo. So now this data frame has all the necessary stuff extracted out. And I already have my unit function to make it work. And let's see how many dates I have. I have around 88 days of data. And how many hours? Of course, 0 to 23. And let's say, can I take one day worth of data and do profiling? So now I finished the feature engineering step or feature processing step. I will go to profiling step. I will pause here because that's the next junction, and we need to be very attentive to that. Is there any questions around it? So we just did our homework, make things ready for the next big process. Okay, so to give a glimpse, we took our data for 10th of February and hour 5, and see there are many rows, and I only took head 5. What does it mean? It means that even in 1 hour, I can have many points. Even in 1 day, 1 hour, I can have many points, because 1 hour has 3600 seconds. I can have data per second. So I can have at least 3600. If I have data coming in per milliseconds, imagine I can have 10,000 records every 1 hour on a given day for a given model. And think about if you combine it for all days, all hours, all models, how big that data can be. Okay, so now we go to the next step. What's the next step? So we need to profile. What is a profile? Profile is generating statistics. While I talk, I will execute these lines. Oh, okay, this is quite fast. Okay, so we use ylogs, and I'll give you an example. I took a February data frame on a particular date, just the one I showed you, and I use ylog to make a profile of that data. Similarly, I took a competing data frame from the next month, March, exactly 1 month later, 10th March, exactly same hour 5, and I also took that data frame. Why I'm taking 2 different data frames? To show that there can be some distribution drifts. And is it possible to visualize it? Yes. How will we do that? Let's look at, first of all, let's use ylog to profile it. So when we use ylog to profile it, what's the output? So we profile only 2 features. So there are 6 features. We only profile 2 features for the demo purpose here. And what does it show? It shows the distribution of only that particular date and hour. What was the distribution of feature 5 and minimum and maximum value and all the quartile values. Similarly, we take exactly if after 1 month, what is the distribution of those features next month. Of course, it is not same, but how different. So, and it will be visibly different. If you see here, max is like 121, here max is like something 16,000 something, and mean and medians are different. Of course, data changes over time. So if we visualize it, again using the ylogs visualizer, and if I just take only one feature to visualize and superimpose this, it will be clear that there is significant distribution drift. But we are not talking about distribution drift today. I'm just highlighting it here to say that data changes over time, and creating the profiles every day and merging it or overlapping it, we can quickly identify things. And this is the basic principle or premise we will use. So now we have like ylogs profile, but this ylogs profile is a kind of a different data type, is kind of a data set profile view. How can I use it? So in order to use it and to incrementally process profiles day by day and merge it, we need to serialize it. So ylogs provides also this serialized method so that you can convert your profile into a binary. And if you convert it into binary, what happens? You can save it into the database and load it back later to reprocess. So we complete the second step, profiling of the data to get statistical matrix out of them. So let's pause here and see if you have any questions on the entire thought process. Yes, yes, please.
When you say that's stored in a database, you're just saying stored in its own database, not stored alongside other. I guess where would you store the serialized data?
So for the features, we have a Hive table. So we will have another Hive table to store these profiles. So the question was, where are we going to, what kind of database? Is it the ylogs database or it is our own database? Did I get the question correct?
Yeah, just where it's stored.
Yeah. So any more questions? So now I showed, like, I took only just 1 day of worth of data for each month and profiled it. How can I scale it? Now the question comes, how to scale it? I have so many days, so many models. The trick to do is, again, the same principle that I followed. Think of the business logic, the unit function. The unit function is to profile a chunk, a partition. So we write a function, and whatever I have talked so far, I've just copy pasted and put that code here, that create the profile, create the view, and serialize in one shot. And what is features DF? Features DF, assume that you have so big data frame, it cannot fit in one machine. So I divided it into partitions, and there are 10 machines. Each partition is this feature DF. Each partition on one executor or node is this chunk. Can I profile that chunk? This is this method, profile features. If I can profile one chunk, I can profile million chunks. And so we write this unit function here, and then we test it. Like, okay, we wrote the function. Can it work? Is it working? How can I test it? I just pass one chunk, 1 day, one chunk, and test it out. I get the profile binary, so I'm confident it will work, and then I will scale it up using Fugue. So how does Fugue help me? Fugue helps me, this cell will take 3 minutes to run on my laptop, but I will explain how it works. So Fugue has this function called transform. What is it transforming? It is transforming this data, the big data we had, using which function? Profile features. It works on one chunk, so it can work on many chunks. And how should I get my chunks? I should divide the entire data partition by these 4 things that I want every day, every hour, every model, every version. For each of these, I want to divide this data. For each of these distinct combination, I want to divide the data into chunks, and I want to profile them for those chunks. So I will take a pause here to kind of see if you have any doubts or questions on till this point.
I have a general question. So I have been looking for logging services for specifically something similar to this. And usually, like the main hurdle between logging and not, or doing logging or not doing logging is like you have to write this extra bit of code to figure out what to log, what to keep, and then also track it.
Mm.
And does ylogs make this process easier or more streamlined? Like, is it less work?
I think ylogs is more on profiling. It will not interfere or dictate how much you log, how much you not log. So that is the decision we take. So for each model, we have a configuration. Like we sample down the number of requests coming in, and then we log it. Ylogs is just for helping us to process later, not live. It's like a post-logged processing so that we can create profiles later.
Okay.
Let me chime in. So, what's the advantage of ylogs? So, in the practical use, we notice it's blazing fast. It's really, really fast. The backend is using C++. And you literally can go like a one scan, and you can get all those metrics. Of course, you can select like what metrics you are really interested in. You can keep them, right? But practically speaking, when you scan this large amount of data, even just keeping all the metrics that the ylogs can log, the data size is still much, much smaller
Okay.
than the original data. And it's still very, very fast.
Okay.
Yeah, but the bottom line is you do have the flexibility to choose, okay, which column I want to profile and what kind of metrics we want to get. But in a lot of cases, you don't know what kind of metrics you will be
Yeah. So
interested
would you
in
say
being like a
it
three
would make
months,
sense
right?
if I was using ylogs, it would make sense to store the entire data set because it takes a while
makes
to
sense.
even decide which features or what I want to log. And the main constraint there is I don't have space or
Yeah,
bandwidth to log everything.
Exactly. We had the same concern, and then we just define it, just keep it simple. Logging everything is still very small, still very fast. I mean, that's just a practical suggestion, but you do have the flexibility to choose what to
Okay.
log.
All right, thank you, Han. So any more questions? So while we were talking, the data was processed, and then you can see it processed like around 300,000 records under 3 minutes. And you can see this binary has been created. Assume that we write another Hive table to store these binaries. So what next? So now if you see the data frame, it's like day, hour, every day, every hour, this model. I have hour profiles for each day, for each model and each version. Can I use it? What's the use? Can I use it for more fundamental, more higher level aggregations? Because we have already the hourly profiles. Can we get a daily profile? If I would have wanted a daily profile, I could have done it by saying, okay, can I re-execute this method just dropping this hour column? It's per day now. Do I need to redo it again? No. Can I use what I have already done? Yes. How can I do that? So for that, we have to use a feature called merge of ylogs. So let's assume that we have, we already know the February ylogs profile for the February data frame chunk. This is like this. Let's say the distribution max is this or mean is this. And we also know for March. So we can check the distribution max is 121. And this is one data frame, this is second data frame. Now, if I want to test, is ylogs good enough? So what did we do? We have two profiles, and then we call the merge method. We have two profiles, merge it, and we'll get a resultant profile. What is the resultant profile? So with max, it is very easy to understand. It is 16,000 something. So in the merge also, if that is the maximum value, I should get that max. So we get that max here for one of the features, for feature 5. Similarly, it will work for the other. So the profiles are merging well. I mean, profiles are merging. I do not know well or good or bad. How can I test it? So in order to test that, we manually now, instead of merging the profiles, we take those two data chunks and merge it ourselves. We are merging the data chunks now. So we are taking the features DF on 10th of March as well as 10th of February as well as March, and on hour 5. And we concat the data frames now. And then if we concat those data frames, and then if we run ylogs profile on those concated data frames, do I get the same statistics? Yeah, I still do get the same statistics. The max and mean are still the same. The medians and mean will still be the same. If you see the median here, you see the median here, it's still the same. What does it show us? That using ylogs on partial profiles and merging partial profiles is equal to processing your entire data frame using ylogs. So we don't need to process your entire data frame. We just process on parts and merge. That's it. That will be good enough for us. So, and how can we put everything in use in real life? So we create a function called, again, the same principle applies. Before going to big data or distributed computing, just think about, can I write a unit work that is independent of each other? If I can write it for one, I can write it for millions. So we create a function called profile reduce, and I will just run it to make it quick. What does this profile reduce do? Assume that you are getting hourly profiles, because we have already profiled our data and it's in Hive and saved. Let's say again we have a Spark job which will take these profiles and partition the data. We do not know how it partition. We decide the partitioning key. Assume that it was partitioned for every model and version and every day. So every day has 24 hours. So at least there will be 24 rows, and each hour can have 1,000 rows. So at least we can expect around 30,000 to 40,000 size per partition. What we do is we calculate the resultant feature by using the simple normal Python reduce function. But instead, what we do is we already got the ylogs profile. We profile it. We take the profile binaries, deserialize it. We serialized it to save it. Now we deserialize it. Once we deserialize it, we merge. Every profile is deserialized and merged. After merging, what we do? We again serialize. So profiles were there, small profiles were there. We took it, deserialize each of them, merge it, reserialize, and save it to the database. It's the same thing we do for predictions, features, as well as predictions. And we also, definitely we need to drop the hour, because we are doing a daily profile and things like that. And once we do that, we will get the result like this. So here you see date. So we have the hourly profile like this. It was the original input data frame, date, hour, model. And then when we do profile reduce onto that data frame, the output is every hour is reduced, and I get just only one for that day. If I can do it for one day, I can do it for any days. How can I do it for any days? Just use Fugue. Just we use the profile reduce function. Now instead of one chunk, I pass the big data frame here, and I do not need hour, and just divide, partition your entire data frame based on DS, model, and version. So every profile is now being deserialized, reduced, merged, serialized, and persisted to the database. So this is where I will stop, and this is the end of the first part of the demo. So that we are using ylogs for profiling. First of all, we did feature engineering, then we did profiling, and then we learned about serialization and deserialization. And after using all of these together, now we can also merge and aggregate and create higher level profiles of these. Now this output is the basis of the next demo, which is the statistical part. So I will pause here and see if there are questions while it is running. It should take 1 minute to finish. Yeah.
Hi, I had a question. So what is the profile providing to Lyft in this case? Is it just for checking for anomalies and model drift, or is that what the next section is about?
Yeah. So the profiling is helping is first of all, it's a distributed way of getting the statistics, because I can we can keep on processing small chunks of data and keep on incrementally merging it. So every day we are processing only 1 day's worth of data. And since we already have the profile for the previous days, we can just keep on merging it. So it helps a lot with the distributed processing and incremental processing. We don't have to like sit and there spin up huge machines to process 1 month worth of data. It's not needed. YLogs is very fast. It uses PyBind under the hood, and going through these profiles and coming back, serializing and deserializing, they use protobuf as well. So it is very fast. It is cost effective, and it runs in very, as you can see, I'm processing 300 records on a Docker machine, under 300,000 records on a Docker machine on my laptop and live. So think about it, how it works in real life. The second thing is, these profiles are itself now has become like time series. Like every hour, this is my profile, or every day, this is my profile. Now these profiles have become time series. Now I can do drift on this time series. If this was my profile last month, this is my profile this month, what is the drift between this? I can keep on doing the drift every month. So I don't have to like recompute everything what happened last month and this month, compare drift, no. The data is already there. I just need to calculate the drift. I can also calculate drift by hour. Last hour, this was my profile. This hour, this is my profile. What's the drift? Because I showed you drift example here, here. We can also forecast, like if this is the mean profile or mean value of a feature last hour, or it was like last 7 hours, can I train a model on this mean and forecast what should be the mean value in the next 7 hours? So when live data comes, can I compare with the projected mean and say it's an anomaly? So that's the second part we will come. But essentially to put, so YLogs gives us a uniform way of processing variety of things, and the resultant profiles itself is a time series which can be leveraged for other things. Okay, so yeah. Oh yeah, sorry.
How effectively does the merge work? And is it just merging on the statistics themselves, or is there additional metadata written in the serialized form that's being used to assist with the merges?
Han, can you answer that question?
Yeah, I can answer that question. Although I'm not the author of bylaws, but I did look into their code. They did maintain some of the metadata. For example, categorical features, right? Categorical features, you can also use bylaws to like a profile them and merge them safely, because they for certain cardinality they still keep the categorical values so that they can merge. And another thing is like, how can you merge like a median, like a two median? How can you merge them together? It's I mean they have some special algorithms to do that. And not only median, actually they keep track of like percentiles, like 99%, 90%, 50%. So actually you really get a very good collection of features that if you want to calculate each of the metric, it will take significant effort to compute. But magically, just with one scan, you get one, and you can merge them. So that's why I think that's a big reason why we choose bylaws. The information loss I'm not seeing is 0%, but it's really very, very small.
All right. If there are no more questions, I will give it to Rajiv. He will talk about the stats forecast application on this same data. Can you talk?
Hello? Oh, okay. Thank you, Anindo. Thank you all for coming. So far we learned about building profiles for the first 40 minutes right now. I wanted to start off, before I go ahead and execute code on this notebook that everybody can do, I wanted to understand, what did all of you get out of profiles? So I want to understand, what is the difference between sampling and profiling? Can anybody tell me what is the difference between sampling and profiling? And why would we choose profiling versus sampling?
I presume profiling is mainly for computing metrics on the sample that has been given. Profiling your model, profiling outputs from some batch jobs, things like that.
Sure. I mean, so you're talking about having profiles built on top of samples that is collected, right? Yeah. So one of the drawbacks of sampling is we miss some of the key metrics. So for example, in anomaly detection, one of the key things we are looking for is finding the one-off thing that we want to catch, right? Sampling, more often than not, tends to have, we basically will miss these one-off anomalies. So with profiling, what happens is we essentially sift through all the logs or data that is given, and we capture all these rare events and build these profiles. It's not it's a common practice across industry to do sampling and then take a mean or median or standard deviation and do anomaly detection. That's not novel. That's not new. But the approach we have taken is to do anomaly detection on profiles, because profiles, as Anindo mentioned in the previous talk, they are easy to maintain, they are mergeable, they're computationally incrementally only, so you basically compute profiles only once a day or once an hour, and then you can go ahead and merge them to get higher granularity profiles, building low granularity profiles. So computationally, it's much less expensive. So for example, if we basically build a huge, let's say we build a mean for a big data set, and then 4 days later, we decide that we want to have the median or we want to have something else, computationally it becomes really expensive. So profiles also help with that. So you have low IO bound problems, computationally less lower bound problems. So, but one of the key things is between sampling and profiling I want to take away here is profiling captures rare events, which is one of the key things for anomaly detection. We want to capture as many rare events as possible. Which profiling helps us to do. And also we want to do it in a way which is economical, right? Theoretically, we can have many solutions, but practically we're all constrained with compute costs and all those things. So we want to have an approach which is scalable and also have a way to capture all of them as much as possible. So having said that, let me go back to this slide quickly. All right. Okay, so in this talk, for the next few minutes, we're going to talk about anomaly detection using the build profiles from the last talk. So we are going to basically focus on using time series forecasting. So we are going to use time series forecasting, univariate time series forecasting for doing anomaly detection. There are various packages out there. In fact, before, we are going to use Nixtala's stats forecast package for doing time series forecasting. Before that, we actually even used Facebook Prophet. We also tried with LinkedIn's Grey Kite. But we actually decided to stick with stats forecast because of its really good performance, as well as a wide range of options in terms of the model selections that you have. It basically provides MSTL, AutoArima, exponential smoothing, ETS, and name it. And all of them are neatly wrapped behind an interface. So if anybody wants to change the way they do anomaly detection on different models, it's just a flip of a model without any change in code. So maintenance is really easy. It's really fast. They actually use Numba and parallel computing behind the scenes to make it really fast. So, so for these reasons, we kind of chose, we kind of stuck with stats forecast. Okay, so once we, so the next step in anomaly detection, once we do forecasting in a univariate forecasting, is we actually have confidence intervals. Confidence intervals gives you the bounds of, so in forecasting gives you a value. Once the value is there, it also gives you a confidence interval, which says how confident this is. we define an anomaly as anything that is outside the confidence interval. That's essentially what we do. So the graph here is an example of what we'll see in the tutorial in the next few minutes. It basically, so the blue line is the prediction value of a model. It's actually is the mean of the prediction value of a model. And the red lines are the highlighted anomalies by the stats, by what we do. Okay, so once this is done, anomaly detection, right? Like, okay, we found anomalies, great. What next? Seldom this is not that useful. Like, okay, we say that there is an anomaly in your model. Okay, they acknowledge that, but the harder problem is, why is there an anomaly? What can we do about it? Can we actually try to give some more context around why the anomalies existed? So there are many reasons why anomalies can happen. In this particular tutorial, we're going to focus on feature drift. Like, we're going to try to understand how a change in feature impacts a change in prediction. For that, we basically try to fit a model, a simple regression model, and then try to explain how that model behaves with shapely values. We're going to go through all these things in the tutorial. Okay. I want to pause here and then ask anybody has any questions so far? Yeah. Cool. Let's go with the demo. Okay. So the first part is we basically read the daily profile. So the daily profile was generated from, oh, sorry, thank you. Is the size okay? Okay. The first part is we basically load the daily profile we generated from the previous talk. And then from then on, we go ahead and define the detector. So I want to pause here and take a minute to explain what this is. So once the profiles are loaded, what do we do? What metric do we choose to do anomaly detection on? So it really depends on what we are interested in. Like, some models have prediction as like numeric predictions. Some have categorical predictions. We have had situations where suddenly there is a new categorical prediction value coming out. We have had situations, numerical predictions are largely the use case for us too. So the first step is to choose what distribution metric that we use to choose to find anomalies on. So for this particular demo, we're going to use mean of the predictions as a metric. I'll go ahead and I'll talk about what is an MSTL detector. So if you're following this tutorial, there is a file called AD demo. This has all the definitions. I'll come to that in a minute. But I just want to basically point out that we're going to choose mean of the predictions as the unit of reporting anomalies on. So in this particular demo, specifically, we have only one model. In reality, these models, as Anindya was pointing, we are basically collecting logs from all the models in a centralized place, coming through Kafka or streaming, and then collecting through logs. And then we sift through them and build profiles. There are like various models in reality. But for this purpose, for this demo purpose, we're going to have only one model. So in this, we are basically seeing that we have a model called demo model, the version date. The dates are like basically daily profile. Because it's a daily profile, you can see the each line corresponds to 1 day of profile. So we have the predictions and the feature profile for each of these. And then we have the total number of records roughly sampled in each of these. So the next step after we decide on what metric to pick on is to extract these profiles. So like you saw about these things in the last talk. So these are the different metrics. We have the preds df basically tells us the predictions df's metrics. So you have a time series of different metrics. We have cardinality, counts, max, min, and all the distribution profiles like mean, median, standard deviation, things like that. And as I said before, we are going to pick the mean for this talk. And then if you look at the features df, the features df is represented a little bit differently. So I'll go back to extract. I'll go back to this function, which is essentially the extract profiles, to see what's going on. So before I go there, so the features df, which is all these, each of these features has our univariate distribution mean values for every single day. So we just decided to pick the mean values for every single feature for this demo. So like if you look at this function here, extract profiles, it's a pretty simple function. We basically take the daily profile created. We go through those profiles. We go through the features profile and the predictions profile for every single day, and for features we capture the mean of them, and for predictions we capture all of them. Because the reason we capture all of them is because it can become. So if I go back here at the very top. You see here we basically define a detector with mean. I can, for example, also, if I'm not happy with this, or if I want to have more things, I can also say something like distribution / median, right? So it gives us the flexibility to do anomaly detection on more than one metric, and we need not do MSTL detector. We can even have, I don't know, auto ARIMA if we have that available. So it gives us the flexibility to choose different models and different metrics on a model basis. And that's the reason we kind of kept all the statistical values for each of the predictions. So once this is done, we essentially extract it out and return the predictions and the features df. Yeah, that's pretty much about the extraction of the profiles. Wanted to pause here a little bit before the next step, because the next step is about generating the forecasts and how we do things. Do we have any questions at this point? Okay, cool. Okay, so once we have these profiles, the next step is actually to generate the forecasts. So I'm going to examine one detector. So in this demo, I have just defined one detector, which is basically the MSTL detector and using the mean. So we're going to extract one particular, we're going to run this function. It's going to take probably 50 seconds or something. While this is running, I would like to go and look at what does score mean. How do we actually do this, right? A detector is basically an MSTL detector. So let's look at this MSTL detector class. So the detector class is a wrapper around the stats forecast that I've written. It basically, we need to specify a few things for stats forecast. One is being what models do we want to use for anomaly detection. In this particular case, we are only going to use MSTL. We are going to tell them what metric on the data frame column that we're going to pass to use. In this case, we're going to use distribution mean. And the level is basically the confidence level. We want to basically ask what confidence level that the stats forecast package should report for the confidence bounds. So we're going to initialize this with this. And once we call the score function, the score function basically is a caller, basically does the actual computing of the forecasts. So what it does is essentially takes the data frame, which is our entire data set, and then it takes the models and frequency. Frequency is basically either it's the daily frequency, hourly frequency, and things like that. So we basically define the frequency of these models. We initialize stats forecast here. And then stats forecast, basically we use this function called forecast. In forecast, we basically specify the horizon. And also one thing, so we basically specify the horizon of the forecast here. Fitted, one unique thing that we really liked is turning fitted equal to true inside stats forecast like the interface gives us in-sample values for the predictions and confidence intervals. Like this is really, really useful because let's say we are working on a month or 2 months old of data and we are forecasting for the next 2 days. Turning fitted equal to true basically gives us in-sample values for forecast and confidence level for all the previous 2 months. So we can go back in history and then basically try to find out where were the anomalies and how to report anomalies on. So this is one of the cool things that is done there. One thing I wanted to mention is also the seasonality. So I'm using MSTL here, which is multiple seasonality trend lows. So the season, it supports multiple seasonality. So for example, let's say you have a daily seasonality, weekly seasonality, and monthly seasonality. So you can specify an array of seasonalities, and then the model actually takes it in and then just computes it. Any model you take is basically wrapped around this score function, because the core or the fundamental way to compute for forecasting is just this function, just this simple function. I'll go back to this and we'll see what the forecasting looks like. So here are the days. The DS represents the dates for each of the days. We basically have Y. The Ys are our actual predictions. So these predictions, remember, are the distribution mean values for this model. MSTL represents the forecasted value from the stats forecast package. MSTL low and MSTL high, these are the confidence bounds. So if you look at the top, we basically specified our confidence bound as 99.9. So you can even basically go as an array and say, like, you can have multiple confidence bounds. So you can try out multiple things at the same time. And the beauty of this is it doesn't take any extra noticeable time. So they have written it so well that it leverages parallel computing and number really well. So adding more seasonality, more number of confidence bounds doesn't take any extra time. Yeah. So I would want to pause here and check if everybody are with me, have any questions on stats forecast or why we chose it or anything else. Okay, cool. Let's move on. So once we define these anomalies, once we define this forecasted data, we're going to try to find anomalies. So as I said, anomalies are anything where we say that if the confidence, basically, if the prediction is not lying within the confidence bounds, we define that as an anomaly. In this particular case, we are not going to use the forecasted value for the next 2 days. I can talk about after this presentation, if we have time. I can talk about like how we are. We have a couple of projects we have lined up where how we are trying to use it for real-time anomaly detection and stuff. Okay, so let's run this. So basically, after running this, we basically found that we scored it, and we tried to find anomalies, and it said that for the mean there are two anomalies at two different discrete times. I want to pause here a little bit and talk about Fugue and why it matters. So far, because this is only a single model, a demo situation with a single model, everything is running fine and things are okay. Now, if we want to, practically, it's not going to be a single model. It's going to be multiple models and lots of data. So what we can do is basically we can leverage Fugue. Fugue basically takes in our daily profile, and we can define this function called Fugue find anomalies. So Fugue find anomalies is a simple function of what we just went through. Like we basically extract the profiles for each of the detectors, we find the anomalies, and return a data frame with the model name and the anomalies. So it is a simple function. This function, as you can see, is very pandas. It is very testable, and basically we can use this function in Fugue to do a distributed computing across multiple models. So if you look at it, so we basically define the daily profile. We use the find anomalies function we defined. We're going to pass in the detectors that we defined at the beginning of this function. And we're going to define the schema, output schema, which is the model name, as well as what is the other thing, which is the anomalies per model name. And we're going to partition the data by model name. In this case, model name is unique enough, where so each model name data will go to one partition. We're going to sort it by date. And I'm saying we are going to use engine as Dask, but if we can even say engine as none, which will basically use pandas. We can say engine as Spark. If we want to use Spark, we can use engine as Ray. The beauty of this is all of these run without the user requiring any explicit changes, thinking in terms of Ray or Spark or anything. All the user does is define the function in terms of pandas, how they understand in a single machine kind of a scenario. And once that is done, they choose a right partition scheme, and then choose your right up engine, and then run it. So, and then so for example, if I say engine has none, I do not need this config, and I can run this. It's basically going to give the same result. It's going to take some time, and it's going to give the same result. So this, to be really honest, Fugue has been a really big game changer across the company for us, because not many people understand how distributed computing works, and probably not many people would want to. Yeah. So Fugue is really good. We can talk about Fugue later too. Okay. So once now that we basically found the anomalies, let's look at how to see those anomalies. As we saw in the presentation, this is how the anomalies look like. The blue line represents the mean of the predictions, and the red line spot the anomalies for the 2 different timestamps we found. Now that we found these anomalies, now what do we do next? How do we analyze what features cause this issue? Can anybody tell me have any thoughts about this? What would you do to analyze which features causes prediction impact? What would you do?
SAP analysis?
What's that?
How does SAP?
SHAP analysis?
SAP or Lime?
Lime analysis. Yeah, exactly. So we do SHAP analysis, but in order to do SHAP analysis, what we do is we want to essentially measure the change in prediction with respect to change in features. So essentially, our dy is going to be the change in predictions, and our dx is going to be the change in features. So if you look at this function, we define our x as the features, our y as the predictions. And what we want to do is we are going to train a regressor saying we want to fit a model where we try to find the change in features with respect to the change in predictions. So this model, we take this model and then use SHAP to explain what this looks like. What the output of this model, essentially what it gives us is the change in features impact to the change in predictions. Because in a stable ML system, right, if you go to this diagram with this blue line, day over day, the mean value of predictions should not drift as much. They will definitely change, but they are not going to jump drastically. What we are trying to measure is the drastic drift in this prediction day over day. And we want to measure that drastic change with respect to change in features. So doing this model training is how we do. So let's look at what happens if we do that. We basically use a bar chart. So what this bar chart tells us is essentially, in this case, feature 5, the change in feature 5 has the highest impact to the change in predictions. So this is something which we are looking to reason out, right? We want to understand which features change made a prediction change at the same time. So in this case, we basically found feature 5 has the highest impact in terms of the prediction output, and other features follow. Now that we know that information, we basically try to find how the features look like at the same time in the same importance. So if you look at this, feature 5 at the same time had the highest, clearly had a big impact, and also at the same, and on the other side of the time frame also there was a big drop, which had a big impact on the model prediction. Feature 6 at the same time had a similar attribution here. Feature 3 not so much, but the model thought that this is change in this was relevant. Feature 1 and again feature 2. So this whole feature importance is based on the importance what we got from the SHAP values. So this kind of comes to the end of my demo, but the key takeaway for this anomaly detection is doing anomaly detection on mean or standard deviation is not anything new, but using profiles to do the same thing, and ability to reason out why there was an anomaly detection, why there was an anomaly on features, has saved many hours across many people, many teams, because most of the time when there's an anomaly, people try to scramble. Many models don't get monitored on a daily basis. Features add in, features drift over time. But ability to reason out quickly and pinpoint so that you can take corrective actions within time has saved us lots and lots of times. And also, one thing I wanted to say is like we do automated anomaly detection, as in when in reality, like every day there are models being written by various teams across the company. We can't have users go and onboard every single model to an anomaly detection system. So we have this centralized way where all the logs come in, they get profiled and automatically get picked up, and then this anomaly detection system runs. We generate the graphs and alerts go off to users based on various settings the users have chosen. With this, I would like to stop. And any questions? Yeah. Sure. Sorry. Yeah.
So thanks for presenting all this.
Sure.
What do you do in order if we had to do like collinearity among the feature reportings?
Sorry, can you repeat?
What would you do if you had to consider a collinearity among the features?
Collinearity among.
So the question is, what would we do if we have to do collinearity on the features? That's a good question.
So we do not have special handling on that. Here is the thing. So think about that like we use SHAP as like a ranking logic to rank from the most important features to less important features. It's not a fact. It's just a method to help us put the nail down the most important feature. But we cannot say it's totally accurate. But as long as it's helpful, as long as roughly it works, as aligned with your common sense, we think it's fine. So we do not have very expensive handling logic. Any step from profiling to this, everything is blazing fast. Because we need to provide, we need to really need to process huge amount of data with a lot of compute power. So I mean, the methodology is not perfect, but as long as it works, like in general, I think we are very satisfied with that.
Yeah, like the idea is to provide solution generically for now, because having specific solutions can be very expensive. Yeah, sorry.
Just go.
Sorry, I can come down. What do you say?
Do you have issues with large number of alerts, like alert storms, and how do you suppress duplicates?
How do we? So the question is, how do we suppress? Oh, I don't know what happened. Okay, so the question is, how do we suppress duplicates and alerts? How do we find duplicates and?
How do you manage the number of alerts? Do you have like alert storms,
So basically, you're trying to find out how do we handle false positives and all those kinds of things. Yeah. So one thing is we choosing good confidence bounds. So having a 95th percentile confidence bound can be very noisy. Based on trial, we basically tried out different algorithms like MSTL, AutoArima with different univariate like mean, standard deviation, and things like that. We basically have fine-tuned that, like based on like trial and error, we have found out that this is the mean with MSTL and AutoArima works best for us. And if some team feels that this is alerting them way too much and creating alert fatigue, we plan to actually give them the ability to pick a different confidence level or a different algorithm also. But for now, with this, we have had reasonable success where we are not alerting way too much. With 3 nines, we don't actually have a lot of false positives for our use case. But again, it depends from case by case basis. Yeah. Does that answer roughly? Yeah. Yes.
With profiles, do you no longer have to keep as much track of the source data? So you have all of this ingestion of the profile information. Do you find yourself just referring to the profiles, or do you get specific questions about your
Got it. Thank you. Thanks for the question. So I'll repeat the question for everybody. So the question was, with profiles, do we have to go back to the data for specific models for specific things, or does it capture everything? So the answer is we do not have to go back. The whole point of profiling is doing exactly what you said. Like, it captures a large variety of econometric models and metrics, functional metrics and distributional metrics, where a user has the ability to pick and choose whatever they want without having the need to recompute anything. So, and also the size of the profiles are really, really small compared to the actual data. So we have never had the need to recompute any of them. Yeah, thanks. Any other questions? Hi, yes.
So in real production systems, like you have in Lyft,
Yeah.
and you say like how basically fast it is.
Yeah.
So what have you seen so far in terms of like latency, in terms of getting back all the results of the profiling? Let's say you started from like day one of implementation, when you have like these billions of records.
Yeah.
What have you seen in terms of like being able to compute all those profiles?
Yeah, so that's a good question. So essentially, there is a setup, like let's say this is the first day I'm writing this system, and I have to backfill data for a year. That has some cost of computation because you have to build profile for a year. But going forward, we basically can have a daily job, which basically builds hourly and daily profiles. It takes about 20 minutes to build the profiles, and it takes about 10 minutes or 10 to 15 minutes to basically get anomalies for all the models across the company. So together we can think of this as a 30-minute job a day to build profiles and find anomaly detection, or do anomalies across all the models. So we're talking about several hundreds of models. And we are also, in terms of the compute cluster, we are using Spark, and roughly around 32 pods with like, yeah.
It really depends on like how many CPUs.
Yeah.
Our normal size for this type of job is like 1,000 per minute. It's not a lot.
Yeah. It's really not that much on a daily basis. Yes. So there was one more. Yeah. Hi.
Following up on the question you were saying that you never have the need to go back to the original data sources themselves. Is the idea like you choose the size and metrics of your profiling so that you never are interested in the individual points that pop into it, so it's kind of fully, there's never, you make sure that your profile is extensive enough that you never want to look at individual observations after? Is that your like rule of thumb for determining how to make a profile and go working here, or is there another
The former, yeah. Like the question was a follow-up on previously. Basically, is the idea that we never want to go back to individual points. Yes, the idea is we don't want to actually go back to individual data points to go and pick on to do anomaly detection on them. The idea is to capture the essence as much. Yeah, Han wants to add something.
Here. So actually to clarify, we do profiling on the full data. We also do sampling. So if you really want to look at some of the sample, inference log, you are able to see that we do sampling. Our expectation is we don't want people to really look at the raw data or even the sample data because that takes a lot of time. Our philosophy is, what is anomaly detection? Anomaly detection is not to help you find a yes or no, but it's to help you, it's to accelerate the process for you to find a yes or no. Right, so this is our design philosophy. So we really want you to look at a minimal amount of information and to make the quickest decision if there is any issue or not. But if you want to like do deep dive, you can look at the sample, and if you want to get the full data, okay, yeah, you can just get the full data from the raw log using SQL. It is also totally fine, but think about that, how long that will take, right? Yeah, our philosophy is if originally it took you like 2 hours to investigate an issue, now 1 minute, you should see, I mean, with business
with the business context as a modeler, as the owner of the model, with the business context, and when you see this chart, you can tell if there is issue or not in 1 minute. I think it's worth it. Yeah, we do not want to make the final decision for you, telling you if there is any issue, because notice this is the first layer of protection. It doesn't mean we do not have other protection. Actually, the first layer is totally unsupervised. The second layer is totally manual. So every model owner, we encourage them to have their manual rules. Because what is manual rule? Manual rule is the business context. So the second layer will incorporate a lot of business context. That will be more accurate. Right. Yeah, so we want a layered protection for our system.
Yeah, like as a platform team, we do not want to be involved in every single team who's building a model. Like we also do not have enough context to be debugging their models. Our job is to basically point them to a direction where there is something wrong, and it's up to individual teams to take it up and then investigate. Any more questions? All right, thank you. I'll hand it off. Yeah, you want to? So I'll hand it off to Anindo to talk about learnings, and if we have time, he can talk about Fugue. Thank you.
Hello. Thanks, Rajiv. So we have one slide. I will just quickly touch on it. Can you hear me? Okay. Yeah. So why did we go through all these steps? Like this is like merging of many things: profiling, engineering, merging, and then stats forecast and things like that. Yeah. So we learned that computing aggregated metrics can be very slow and cost prohibitive. You all know. I'm sure you have faced these challenges. And incremental processing day by day makes it more. We want to have a cost-effective way of doing things. So this mechanism helped us to do this effectively, and also this aggregation matrix after profiling gives you a clear sign of seasonality and cycles in the metric of your choice. And then we later correlate like the delta dy, the delta of prediction, with dx, the delta of feature drift. And so there's a basic way of protecting the system, as Han was mentioning. Yeah, so we are at this stage, and we will use this. We are working on using this fundamental piece in like other areas, like Rajiv mentioned, like real time, like as the data is streaming in, if we have the forecast from previous profile data, can we detect anomaly on the fly? Yeah. So I will stop here, and there is one quick.
I wanted to add one thing, Anindo. So like we showed all this with respect to in context of models, machine learning models. But if you think about this in reality, this is just a univariate time series, which is applicable to a wide range of contexts. So for example, we are even using this for business metric analysis. For example, operations team, they have tons and tons of univariate time data. And reporting anomalies on that is really, really useful, because they basically find this really useful. So that is one aspect. So any problem in a company that can be modeled to a univariate time series can be applied to this solution. Can be applied. We are even applying this to real-time anomaly detection, where we use the generated forecasts for the next day, and then in the next day when the events are happening, we actually compare what was generated yesterday and try to report anomalies. So like these are some of the interesting things that can be done.
Yeah, thanks, Rajiv. And while we are talking, so if some of you have been careful, observe that I ran some 3 cells. What was that? So we talk about like scaling up using Spark, Ray, or Dask. So here is an example. I just took the first notebook and just changed the engine to Dask. It is an example how Fugue transform can use Dask on a notebook which is running on a Docker engine to distribute the parallelism. I can see at least there are 3 repetitions of this block, so 3 processes spinning up under the hood. And it is using Dask to split the data into partitions. and it is still computing. It will take 1 minute, and if you were careful, this cell errored out at some point of time. If a live demo doesn't have an error, then it does not make a demo worth. So that's what happened. So I fixed it, and it will run it in 1 minute. So yeah, we can take more questions. This is our end of the demo, and we can take additional questions.
Install Fugue in your do you install Fugue in your ecosystem, say AWS or whatever other Google or any other ecosystem you're in?
Yeah, it's a great question actually. It digresses into a different topic, but it's a great question. So we usually use Spark. Most of our processing is on Spark. So we have custom Spark image for us. So where that Docker image contains Spark as well as Fugue, as well as other libraries along with it. So when we spawn the Spark executors, and we had a talk last Databricks AI Summit, how we use Spark on Kubernetes. But the TLDR is, we have many executors. Each of the executors is based on a custom image, which has Fugue, MSTL, the stats forecast, everything installed in each of these so that they can process each of these data. Yeah, so the task has also completed as we speak.
Thank you.
Any other questions?
Okay, all right. Thank you, folks, for coming in, and the codes are already public. And let us know if you want to chat more about it. We are here. We can be. Oh.
All right, thank you.